So let's start our next session. So before we start this, how many of you are, how many of you were already familiar with parameterized complexity before the morning session? Okay, great. So how many of you are now familiar with parameterized complexity after the morning session? To some extent. Okay. So basically in the morning session, what was the idea is exploit some parameter of problem and design efficient algorithm with with exponential term only in the parameter, right? So that was the idea. But now this session is about hardness in those type of running time as well. So I hope all of us are familiar with NP hardness now. Yes? Okay, so NP hardness and NP complete. I will assume that we all know about it now. Okay, so let's start. So what we will talk about in this session is I will just introduce this notion of hardness, and then I will introduce something which is called parameterized reduction, and then we will look at some problems like independent set, click, click on regular graphs, partial vertex cover, multicolored click, dominating set. So some of this problem, I think definition we have already seen, not all, but some of these problems we have seen definitions in our previous sessions. For example, independent set definitely we have seen, right? Dominating set we have seen. Uh, so what I think will be new, click also I hope we have seen. Yes. So partial vertex cover I think is something new that we will be seeing. It is a variant of vertex cover, something different from vertex cover. So we will see all these problems in this session. Okay, so let's start. So till now what we have done, we have looked at some polynomial time algorithms for some problems. Then we have seen the notion of NP hardness or NP completeness. And then we went on for designing some exact exponential algorithm, something constant power n type of algorithm we saw. And in the morning session today, we saw designing some fixed parameter tractable algorithm, right? So that means function of k and polynomial in the input. This type of algorithm we were trying to design. Okay. So now the question is it always possible to design such running time algorithm? Like, can there be problems where are some particular parameters that we are trying to exploit that we are not able to design such running time algorithms? We are not able to, so if k is my parameter and say n is my input size, then I'm not able to design such running time algorithm. So can we think about that now? That is it always possible or we get stuck sometimes? So is anyone already familiar with this notion here? Okay, so some of you are. Great. So before we move to answering this question, then let us go back and look at how did we prove our NP hardness. Okay, so basically the answer is no. For some problems we are not able to do that. But how do we go about it? How do we show an evidence that we cannot do that? Right. So let's go back to our basics of NP hardness and then we will come back to answering this question. Okay. So does anybody want to answer how did we prove that a problem is NP hard or NP complete? So definition is here, but still, like what did we do? Reduction from one problem to other problem. So we took a hard problem, which we already knew was hard, and we reduced to the problem we wanted to show is hard or not, right? That is what we did. So what was the running time for our reduction that we considered? Polynomial, right? And we had to make sure this third condition that I have written here, that yes instance, the equivalence between both the problems we are reducing. So if we start from a problem P and we reduce to a problem Q and I was an instant of problem P, and I prime is the reduced instance of problem Q, then we showed this equivalence that I is a yes instance of P if and only if I prime is a yes instance of Q. Right? We showed this was part of our correctness. Right? So why did this reduction work to begin with? We said that, okay, we will start with an NP hard problem, some hard problem, and we will show our problem is hard by reducing from there. So why did this reduction work? Because we are assuming something. We are assuming a hypothesis, which is P is not equals to NP. Right? That's what we assumed. That, okay, if I'm reducing from hard problem to me, then if I can solve myself in polynomial time, I can solve the other problem also in polynomial time. Right? And then we are breaking this conjecture somehow. And that's why if any problem, any NP hard problem you are able to solve in polynomial time, you will end up solving all the NP problems in P. Right? So we assume this conjecture there that P is not equals to NP, and by that we are trying to show this hardness. Right? There is some assumption involved here. But so now if we want to show that, okay, some running time function of K and polynomial in our input is not possible, then can we use this polynomial time reductions that we use there? So any thoughts on that? Can we use this? We can. So if we are able to use that, anybody else have any other answers that they can think of? What will go wrong? What will, or is it like completely fine? We don't see any issue. Anybody else wants to say something? Okay, so those minor details we will come to. So anybody else? So parameter, sorry. Yes, so that's true. If we are reducing in polynomial time, we have to make sure that this parameter does not increase too much. Okay. So first thing is our polynomial time reduction guaranteeing to us that. Are we getting that guarantee by using our polynomial time reduction that this parameter does not increase by too much? Okay, that is one question to think of. Second question I would say is the running time. Does it make sense to just allow polynomial time running time in our reduction if we are like planning to anyway give FPT running time to reduce problem? Does it make sense? So here we are putting this restriction that take polynomial time only, because what is happening basically is if we start from P, we go to problem Q and we end up solving it in polynomial time, and if this reduction is polynomial time, then the complete running time is polynomial and we can answer for the problem P as well. Right? So that is why we were allowing polynomial time. But now, if we think of this type of running time, like relax it a bit, we can allow more than polynomial time, right? So let's come to that definition. But let us first try to resolve this issue. That should we, how should we look at the parameter? Okay. So let's look at the example of independent set and vertex cover problem. What we know this, if we look at the NP hardness setting, then both of these problem are kind of equivalent in the sense of hardness, right? Because what is vertex cover? We are looking for a set such that each edge is incident on one of these solution vertices, right? That is what is vertex cover. And if we look at the vertices that are not part of vertex cover, they do not have any edge here, right? So this is an independent set in the graph. So if I have k size of vertex cover, then the remaining part is n minus k if n are the total number of vertices in the graph, right? So if I can solve vertex cover, minimum vertex cover in polynomial, at the same time I am maximizing this independent set and I can answer the maximum independent set also in polynomial time. So in the sense, these two problems are equivalent in the NP hardness setting, right? But when we look at fixed parameters tractable setting or parameterized setting, then these two problems are not equivalent. While for vertex cover, we can design simple branching algorithm. We cannot do that for independent set problem. An independent set problem is very well known to be not FPT. Okay, so if we just consider solution size as a parameter, then vertex cover is known to be FPT, but we cannot design any FPT algorithm for independent set problem. Okay, then even though simply we were able to solve in in NP hardness setting, that see just by the simple observation that K vertex cover implies n minus k size independent set and vice versa, and both this problem must be equivalent in the NP hardness setting. This clear is not the case in the parameterized setting. Okay, so what is the notion of our reduction we should be using? That is the appropriate notion of reduction is the first question. The other question is what is the appropriate hypothesis we should be using? Because there we are using suppose P is not equals to NP, right? What we should use here? So let's come to this. So for this, we have something, a notion of parameterized reduction. And what does it say? That if we have two parameterized problem P and Q, so so we are trying to reduce the parameterized problem P from Q. And what is the parameterized reduction property we are looking for? That suppose you are given an instance I comma k of P. So I is my classical instance and k is my parameter. For example, in vertex cover, we have a graph G and k is my solution size as a parameter we are considering. Okay, so G comma k is a parameter is an instance of a vertex cover problem, right? So suppose we start with a problem and we are able to construct an instance of problem Q. Say I prime k prime is my instance of problem Q. Then what is the condition we want on this reduction? Firstly, the correctness, right? Because if we want to say something about the problem Q, we should have this yes and yes, if and only if condition. So like our polynomial reductions, here also we imply this condition that Ik is a yes instance of P, if and only if I prime k prime is a yes instance of Q. Okay. Now the other problem that we said that parameter should not increase a lot. For example, in a vertex cover an independent set, k goes to n minus k, right? K size solution for vertex cover implies n minus k size for independent set. But it is some function of n. It is not just function of solution size k. That we do not want to happen, because let us look at the problem P and the problem Q. If my parameter was not function of k and some function of n, then all we are able to say is that okay, some function of n algorithm is there or not. It is not, we are not able to imply anything for the parameter k for P, right? We are not able to say. Even if I have some function of n algorithm for Q, what did we say about the problem P? Nothing, right? How did we, sorry, the other way around. Right. So if I start from a problem P and I reduce to a problem Q, and we know that for the problem P, some function of k and power order and one algorithm does not exist where k is my parameter. And now for problem Q, my parameter is say some function of n, right? Then we were not able to imply anything for problem Q here by saying that, okay, does problem Q also does not have function of k and power order 1 algorithm? We don't know, because all we are trying to design is some function of parameter and polynomial in input time algorithm. So, but if I had, say here, some function of k as a parameter, then I can say that, okay, if I'm able to design some function of k and say whatever the polynomial in input running time I have for q, then I should not be able to design such algorithm for P as well, and which satisfies our conjecture to begin with that, okay, we know that P does not have such algorithm. So we are doing some correct thing, right? If whatever we are implying is already known to be correct, then we are in good hands. So this is one thing. Now the other is the running time of our reduction. So there we were allowing a polynomial running time in anti-hardness reduction. Here we can allow something more than polynomial, right? Because if we start from problem P and we reach problem Q by some FPT running time, then even if we add up this FPT running time to whatever the running time we need to solve the problem Q, it still is FPT. FPT plus these two functions will still give me some function of K and polynomial in input of P running time, right? Huh? Say X is the input of problem P. So as I'm using N, but here I have written X. So X is say in polynomial of, sorry, the size of the input of the problem P. Okay. So what did we say here is that, okay, if we allow this much running time, then also nothing goes wrong. So polynomial is too strict for the running time for this reduction. We can allow much more than that. So even if we're reducing from problem P to problem Q, and we are using this FPT running time, we are still able to say that, okay, see, you should not be able to solve the problem Q in FPT running time because this total is FPT, and then you should be able to answer problem P in FPT running time, but you would have started with a hard problem. So this should not be possible, right? So this is the parameterized reduction that we will be using, the definition. So what we want, first we want the equivalent, that, okay, if you start with a hard problem, and whatever the problem you are reducing to, both the instances should be equivalent. Ik is a yes instance of P if and only if I prime K prime is a yes instance of Q. And the parameter that your problem Q have should be some function of the problem P, some function of the parameter of the problem P. And finally, the running time of reduction should be some FPT in the FPT for problem P, some FPT running time for problem P. So let's just pause here. Any questions for this? So is the idea of reduction clear that we will be using? Yes? Okay. So now let's come to the second question. What is the hypothesis we should be using? Now we do not want to use P is not equals to NP because that is not able to say anything about why FPT running time should not be there, right? Because FPT running time is way more than polynomial running time. We are allowing an exponential function there in terms of our parameter. So let's not go into the technical details of what original W hardness terms, which some of you are familiar with. We will be using this hypothesis for the purpose of this talk. Okay. So what is this? That independent set where input is a graph G and parameter is the solution size K. It cannot be solved in time, function of K and polynomial in N, where N is the number of vertices in G. So independent set problem is we have a graph G and an integer K, and we want to find K vertices which do not have any edge between them. Right? So that was our independent set problem. And here we are saying that this problem, we cannot solve it in some function of K and N power order 1. That is polynomial in N, which is number of vertices in the graph G. Okay. So here when we are talking about function of K, we are talking about any exponential function. Say K power, K power, K power, K, any exponential in K. We don't care. But no function of K polynomial in N should be possible. Okay. So this is what we will assume, and we will show that certain problems are as hard as independent set problem. Okay. So let's start with the click problem itself. How many of you know what is a click? Can anybody tell me the definition? What is a click? Yes. So if we look at the independent set, every pair should not have an edge. And in click, every pair should have an edge, like a complete graph. Okay? Every pair should be connected with each other. Okay. So in the click problem, we are given a graph G and an integer K, and we have to find a set of vertices which induces a click in the graph. A simple example of click. This is a click on 3 vertices. This is a click on 4 vertices, and so on. Okay. So now the question is, can we show that click is not FPT? That means we cannot design any algorithm with this running time. So here n is the number of vertices in G. Can you think of something like how do we go about this? Like go back to our parameterized reduction and see that what can we do? Yes. I couldn't hear you. Can you just be a little, please? Please take the mic. So you are saying that divide the into k parts such that this k are adjacent and others are not. So that you are like, that is the problem. Like, can you find such k vertices which are adjacent with each other? We don't care what the others have the property with. Maybe they are adjacent or not adjacent. Complete graph minus the given graph. Mm-hmm. Hmm. Right. So this is exactly the idea we will use, but I will just change the terminologies. So what he is saying, uh, complete graph minus the current graph, which exactly means that complement the graph you have currently, right? So what we will do to show that um, the click is not FPT, we will start from an independent set problem, which we already know that it is not FPT. And we will construct an instance of the click problem. We will show a parameterized reduction by taking the input graph of the G, by taking the complement of the input graph of the G of independent set problem. Okay. So what did we do? Whatever edges are present in the graph G, we remove them, and whatever the edges are not present in the graph G, we added them to our complement graph. So for an example, you can see here that G complement is satisfying that property here. Okay. So is the construction clear? And K goes to K. The parameter is K. So let's go and see, are we satisfying all the property of our parameterized reduction? Running time, yes, because it is just taking polynomial, some inches to for going over all the edges and checking is it present or not and adding accordingly, right? So running time is fine. Parameter is k is going to k, so we are satisfying that function of k. The parameter in the reduced instance, the parameter should be function of k. That also we are satisfying. So now what is remaining to prove? The equivalence. Okay. So basically this, that gk is a yes instance of independent set if and only if g complement k is a yes instance of click problem. So does anybody wants to say why the correctness holds? Let's start with the forward direction. Suppose I give you an independent set of size k in G. What can you say about the reduced instance? Yes. So because what did we do in the complement graph? We removed all the edges which are present in G and added all the edges which are not present in G. So if I have an independent set in G, they will become a clique in the graph G complement because all these edges are present now. Right? So for example, here if you see V1, V4, they have an edge between them. Right? And so this forward direction is okay. Now can you simply say the backward direction also holds similarly? Right? Because if I give you a clique of size k in the G complement graph, that by our construction is an independent set in the graph G. Right? So then if we have a solution here, we can find a solution there and vice versa. Okay? So now we have proved that we have proved our reduction that we can reduce the independent set problem to our clique problem, and which implies that clique is as hard as independent set problem. Right? Yes. An FPT complete problem. Yes. So there is a notion of W hierarchy. So those are the technical terms we are not considering, but independent set is known to be W1 complete problem. Okay. So you can see here, right? If now I can design some algorithm with running time f power k and power order 1 for clique, then I can use this to answer my independent set problem as well, right? So simply we have said that you should not be able to design such algorithm for the clique problem. So clique should be as hard as the independent set problem. Okay. So this was an easy reduction. Now, if you had started with clique problem, you could have done the same thing, right? And you could have reduced to independent set problem, and then you can say independent set is as hard as the clique problem, right? So actually both of this problem we can say are equivalent here in the hardness notion. Okay. So in our further reductions, we will use both these problems alternatively. So we can always do this. We can, if I have proved that clique is hard in this type of variant, we are able to prove that independent set is also hard in that type of variant. Okay. So we can use, we will use this alternatively in our next reductions. Okay. So now I want to say, so we have shown that clique is hard. We cannot solve the clique problem in FPT running time. But what about if we restrict our graph class? If we restrict our input graph class to something which is known as regular graphs. So what is the regular graph? Each vertex, all the vertices have same degree. So for example, this is a 2 regular graph. Every vertex have degree 2. Okay. So now what I want to show you that in fact solving clique in regular graph is also not possible in function of k and polynomial in n running time. So if we are parameterizing by just solution size, then also this problem is hard. Okay. So how we will show this? We will start from the clique problem and we will reduce to clique on regular graph problem. So we will start with any clique in any graph, any arbitrary graph that is given to us an input. There's no condition on that. And we will reduce to clique on regular graph where every vertex will have same degree. Okay. So let's start here. What will we do? We will make d many copies of the graph G, that is input to clique problem. Okay. And after, so suppose G was my input graph to clique. Then for clique on regular graphs, I made d copies for the graph G, G1, G2, GD. And for each of the vertex, I will add a set of vertices UV. So for each vertex V in G, we will add UV, a set of vertices of size D minus degree of V. So suppose here the vertex U was of degree say 5. I will add here n minus 5 vertices. Okay, I'm just giving an example that whatever the degree was, I will just add degree minus that vertex, that many vertices. So I am like compensating for the degrees that this vertex didn't have. Okay, so to make it like all the vertices, the whatever the maximum degree d was, I am adding this dummy vertices. Okay, so when I said the copy of the graph G, it is exactly same as the graph G, or whatever the adjacencies were present in the original graph, that will also be present in G1, that will also be present in GD. Okay. So what we will do, whatever the dummy vertices we have added, we will make them adjacent to all of its copies. So this set UU, we will add it to all the copies of U in all my G1, G2, GD. Okay. So this UW, which had size D minus degree of W, we added all these vertices to all the copies of W. Okay. So this is my construction. Okay. Now to begin with, now can you see that in my reduced graph, all the vertices have degree D? Yes, because of the dummy vertices. We made sure that degree is D. Now the other question is, can the dummy vertices ever be participating in a clique? So the smallest size clique, suppose we are considering a triangle. Can they ever participate in any triangle? No. Why? Because they are only adjacent to their copies. Their copies don't have any adjacencies between them. I did not say that I will draw an edge between U to U. No, I did not say that. So we will not be doing that. And within them also, we did not add any edges. Right? So if any edge is going out of a vertex, there is no way that we can take a path from here to here and come back to this vertex and make a triangle. Or we can make a triangle like this. We can go up, take two vertices from this set dummy vertices, and then come down. This is not, by our construction, that is not possible. So basically what is happening, all these dummy vertices are never part of any clique. If it is not part of even a triangle, how will it be part of any larger size clique? Right? Because to be part of a larger size clique, first it have to be part of triangle also inside that. So clique on 4 vertices also contains triangle. Right? So now if I had any clique in the graph G on k vertices, that will be present in G1 because it is just a copy. That will be present in G2. That will be present in GD. Right? And in the backward direction, if I had any clique in the reduced graph, it will be completely contained inside one GI. And in fact, in all of this GI. Because what did we say? Dummy vertices are never part of any clique. Right? So whatever the clique in the reduced graph will be, the original graph also will have that clique. Right? So what did we show here? That we can reduce from clique in general graphs to clique in regular graphs. Right? Regular graph means all the vertices have same degree. We don't know what it is, like it can be some high number, but what the reduction here, we use that, okay, take the maximum degree and make every vertex maximum degree. Right? So that is what says that clique on regular graph is not FPT, parameterized by the solution size. Okay. So we will use this problem, click on regular graphs. Yes. Yes. How much space we require? So it depends on what is the output size you have. So, yes. Right. So if you look at our running time, that also implies space. Because to use up any space, we will have to construct the instance, right? In that much space, for that much space. And if our running time is like some function of k polynomial in n, only that much space we can use ever. We can never use more than that. Right? Because what if we are using, say, some 2 power n space, then we would have constructed the instance in 2 power n time, right? Which is not allowed in our parameterized reduction. So we are using as much space as, like, say, our running time is required. Does that answer your question? So all it is required to for us to show that how much time this reduction is taking. To add each vertex also it is taking some time in our reduction, right? To add each of this edge also we are taking some time. So all we have, okay, this reduction took this much time. That will answer our space question also. Okay. Yes. So what did we do? For every vertex, we added the maximum degree minus the current degree vertices, and we made them adjacent to all the copies. So now every vertex have maximum degree. So U is present in G1, U is also present in GT. So yes, so we made them adjacent to this capital UU. No, no. We only added the edges from the dummy vertices to its corresponding copy vertices. Okay? Okay. What we are doing for? So the parameter is k only for the reduced instance. Sorry. So if k is constant, then all you are asking for is a polynomial time algorithm, right? That depends on how hard the problem is in the classical setting, right? So if we are asking for just some constant size solution, some k is like some say 100 also, then that we can do always by taking brute force n power 100, right? So that does not make much sense here. Yes. Okay. As I said earlier, we can also show this for independent set and regular graphs, right? We can use the similar ideas that we use for the independent set and click reduction. And we can also show the similar by similar techniques that actually independent set on regular graphs is also hard. Okay. And that is the idea we will use for our next problem that, uh, sorry. Okay. So that we will use for our next problem, which is partial vertex cover. So are we all familiar with vertex cover now? What is the vertex cover problem? We are given a graph G and we want to find k vertices which covers all the edges. All the edges in the graph. Every edge should have at least one endpoint in the solution. Right? So we are covering edges using vertices. Now here in partial vertex cover, we do not want to cover all the edges. We are saying that, okay, just cover some t many edges. I will give you an input integer t. Don't cover all the edges in the graph, just cover some t many edges. Okay, so we are given a graph G, two integers k and t, and the problem asks that find k vertices that covers t edges. Okay, so now my question is, if you take a set of vertices, when you can say that it will cover the largest number of edges? So let me make my question more clear. Consider some graph. Okay. Uh, can you tell me what is the vertex cover here? 3. Okay. So I can see that 1, 2, and 4 is a vertex cover, right? Which are covering, say, 1, 2, 3, 4 edges, 4, 5, 6 edges, right? Okay. Um, so this is also a vertex cover, 1, 3, 4. Okay. Both of them are vertex cover. Now, if you look at both of these vertex covers, so let us see that how many vertex edges they are covering outside of them. Okay. They are covering, say, 4 edges. Yeah, I mean internal edges, they have 2 here, but outside they have 1, 2, 3, 4 edges. Okay. And if I'll consider this set 1, 3, 4, then they have more edges which are going outside of them, right? I want you to use this idea for covering T edges. Right now, this example that I have drawn, we are just getting a vertex cover which is covering all the edges. But if you had to cover T edges, what will you prefer to have? Like more edges within them or more edges outside? Hmm? Outside, huh? Between them. Yes, so we want that if they are anyway covering, we want to cover T edges, it will be better that they go on and cover outside more edges. Because if I had one edge here, I will count only once for it. I will not count twice for it. For both the vertices, I can only count once. But if both of them had seen like instead of each other, one neighbor outside, then I could count 2 for their coverage. Whatever the degree they have, if they are not seeing each other, then for each of them, I can count their degree for the coverage plus 1, right? Uh, in this case, if they had an edge between them, I'm counting whatever the sum of their degree minus 1 because this edge is repeated between them, right? But if I didn't have this edge, then I am counting like sum of both the degrees, right? So both of this, if this edge is not present, then if the degree of both the vertices are D, then I can cover 2D edges, right? But if they had an edge between them, then we are only counting 2D minus 1 edge, right? So let us use this idea for our partial vertex cover reduction, that what we want is, we want them to maximize the coverage, then it is better that they do not have much edges between them. What is the worst? What is the best case? Independent set. They don't have any edge between them, right? That will be the best for us. Now, think of how we will reduce from independent set to this problem. So we know that independent set on regular graphs is not FPT. Okay. Now, can we design an instance for our partial vertex cover problem? Any thoughts? So for independent set on regular graphs, say it is R regular. And as an input, we have given a graph G, which is R regular and an integer key. So now the question is, create an instance of partial vertex cover. So recall that, sorry. No, depends on what parameter we are deciding. So for the partial vertex cover, our parameter is, the problem we are doing right now is parameterized by solution size K. So we have to design an instance G prime K prime T. What are you suggesting? Which one is what? T should be all the edges. So if you keep T as all the edges, you want like vertex cover basically. It's not partial vertex cover then. If T is equals to your all the edges, all you're asking is give me a reduction from independent set on regular graphs to vertex cover, which we said that did not make sense, right? Because vertex cover is FPT and independent set is not. Yes. G dash equals to G. Okay. Hmm. Okay. So you got the idea correct. That what? Let's try this. That let's keep this. Let's keep this as our instance for partial vertex cover problem. Our graph is G, parameter is K, and T, the number of edges we want to cover, is R into K. Okay. So our parameter is solution size k. Parameter is not the t, which is r into k. Okay. So in independent set also, r is not part of parameter, only k is part of parameter. Okay. Okay. So now with running time is fine because we took some polynomial running time for our reduction. Our our parameter is also fine because k goes to k. So that is also bounded by function of k. Now we have to show the equivalence. So can somebody wants to try, say forward direction. If I have an independent set of size k, what can I say about partial vertex cover? Yes, k. Yes. So if I have an independent set of size k in G, whatever my independent set is, if I look at it, if I look the edges incident on them, since each of the vertex have degree r, if I sum up all these edges, then that will be r into whatever my independent set size is, which is k. So if I can find a solution k for independent set, I can also find a solution for my partial vertex cover reduced instance, right? Now what about the reverse direction? Suppose I give you a k size set which covers rk into rk many edges. Hmm? Sorry, k by r, k by t. I didn't get what you are saying. It becomes a ratio of that. No, it does not. Hmm. Yes, it has to be an independent set. Exactly. So both of you are right. If whatever my solution to partial vertex cover is, if they had any edge between them, then I'm not actually covering RK. Each of them have degree exactly R, right? So if they have an edge between them, I'm counting only once for that edge. But I should be counting twice in order to cover RK many edges, right? So if I have a solution to partial vertex cover, the same set I can use for independent set as of independent set of size K. Okay? So is this reduction clear? Okay. So now let's move to our next problem, which is a multicolored click. So we all know click is like K, for K size click is all the vertices have an edge between them. Okay. In multicolored click, here our vertices are partitioned into K color classes. Okay. And instead of asking any arbitrary K size click, we want this colorful click. For each color, we should have a vertex in our click. Okay, so if V1, V2, Vk are my vertex color classes, then from V1 I want one vertex, V2 I want one vertex, V3 I want one vertex. Similarly, Vk I want one vertex. So this will be a colorful click. So instead of outputting any click, we want output a K color click. Okay. Yes. It is given as input. So in the input, you will be given this color classes and you have to output a K size. Suppose you have given K color classes, then you have to output a click which contains one vertex from each of the color class. Okay, so that is the multicolor click problem. Yes, so as an input, we are given graph with K colors. Every vertex is assigned some color and we have K colors. Now the question is, does there exist a click of size K which contains one vertex from each color? Okay. And we do not have multiple colors assigned to each vertex, exactly one color assigned to each vertex. Okay. So it turns out that even this variant of click problem is hard and we can show a reduction from click to multicolored click. Okay. So let me go over this reduction because then we will use the idea that multicolor click is hard and we will show that other problem is hard. Yes. exactly one vertex from each color. We don't this from a color class, because if we are looking for k size click and we have exactly k color classes, then we can only take exactly one vertex from each color, right? Uh, Click containing one. Okay, I might have written it ambiguously, but this is uh, it is that from each color class take exactly one vertex into solution. Okay. So is the problem definition clear? Okay. So any idea how we can reduce the click to multicolored click problem? Hmm. 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 Yes. So that is the idea we will use. You were saying something. Chromatic number is a different problem. It is like finding how many colors we can how many colors we can use to color the graph so that same color vertices are not adjacent. That hmm. Graph between an edge could be uh, it need not be for the multicolored click problem. All you are asking for is give me vertices from different colors as a click in the click problem. Yes. So it does not matter if the same color class have an edges also, right? Because we are not gonna pick two of them together anyway, right? Okay. So as she suggested, this is what we will do. We will start from our graph G, and this is how we will reduce. First, add k copies of this vertex set. Okay. Then, suppose UV was an edge in my graph G. Then I will take the copy of U in all the sets, copy of V in all sets, make those copies adjacent. So here you can see that UV is an edge. So we have made say U1 here adjacent to V2, and we have made it adjacent to VK and so on. So when I said make it adjacent to copies, it should not be in the same class. I mean, we have made like k parts, right? K copies, so it should not be in the same part. So we don't want to make U1 adjacent to V1. We will only make U1 adjacent to remaining copies V2, V3, VK. Okay. So if you look at each set V1, V2, VK, they are not adjacent to each other. So this large V1, V2, VK, these sets are not adjacent to each other. But across we have made all the adjacencies that were present in the graph G. Okay. So if you look at UW, then we will take U1, make it adjacent to all the WIs except W1. We will take W1, make it adjacent to all the UIs except U1. Okay. So this is my construction. Is the construction clear? Yes? Okay. So now can you tell me that, so running time is fine. We are taking, what is our running time? We are taking some n into whatever the number of edges into k running, whatever the number of edges um, into k running time, something like that. So it is still polynomial. We are not doing much. Our parameter is also k to k. Okay. Now the question is the equivalence. Okay. Now can you try forward direction? If I had a click in original graph G, how will you give a multicolored click? So suppose you had some x1, x2, x3, xk vertices. This is a click in the graph G. Can you give me a multicolored click in the reduced instance? So let's come to the basic. So here you can say that UVW is a click of size 3, right? Can you give me this click in this reduced instance? Yes. Yes. I cannot see. Ah, okay. Mhm. Same UVW in the different partition. Yes. So what he is saying is, how can we find, take U1, take V2, take W3. All of these three will be adjacent to each other because we said that across we will add all the edges, right? So here we found a triangle. Similarly, if I had a K size click, I can take one copy of these vertices from each of these colors, V1, V2, Vk, and then I can say that, okay, that is also a click because of our construction, right? Okay. In the backward direction, you can see that we are not able to pick two vertices from the same color because they don't have any adjacencies between them, right? So for the click, we have to pick one vertex from each of the color class, and then we can just go on and take their original vertices from the graph G. Also, by our construction, U1 is not adjacent to U2. So from two color classes, we are always picking two distinct vertices. If we have picked U1 from V1, then we are not picking U2 from V2 because they don't have any edge between them, right? So if I have K multicolored click, then I can always find a K size click in my original graph G for my input for the click problem, right? So here we have shown an equivalence between these two problems. Not equivalence, but we have showed that multicolor click is also hard. We cannot solve it in FPT time function of K polynomial in N. Okay. So now again, what I said about independent set problem, we can similarly show that multicolor independent set is also not FPT. Okay. Multicolor independent set is just find colorful independent set. We have given a K colored graph and we want the independent set to pick one vertex from each color, exactly one vertex from each color class. Okay. And we will use that to show that dominating set problem is also hard. Okay. So you have seen the dominating set problem in your NP hard session. Does anybody remember the definition? Yes. So for every vertex, either vertex itself is in solution or one of its neighbor is in solution. So the solution should be able to dominate every vertex. Okay. So that is the dominating set problem. And we are given a graph G in an integer K. We want a solution of size at most K, which dominate every vertex in the graph. Okay. So basically from close neighborhood of a vertex, at least one vertex must be present in solution. Vertex itself or one of its neighbor. Okay. So now we want to show a parameterized reduction from multicolored independent set to dominating set problem. Any idea what we can try here? It is a bit tricky, but can you think of something? Okay, so let's not waste any time. Let me tell you the reduction. So what we will do, we have this K color classes, right? V1, V2, Vk. Okay. What we will do for each of these color classes, first we have added this vertices xi, yi. Okay. So for V1, we have added x1, V1, x1, y1. For x2, we have V2, we have added x2, y2, and so on. For Vk, we have added xk, yk. Okay. And we make them adjacent to all these vertices in VIs. So xi, yi is adjacent to everything in Vi. Okay. So all the adjacencies are present there. And then what we will do, for every edge that goes across, we will introduce a new vertex. So if I had an edge UV in my graph, then so U will be belonging to some vertex at Vi, and say V is belonging to some vertex at Vj. Then we will add a vertex We, say this edge is, say E is, edge E is UV edge. Then we will introduce a vertex We, which connects to on exactly these two vertices. So We is adjacent to U and it is adjacent to V. So for every such edge, I have introduced this vertex We, and I have made it adjacent to both the endpoints. Okay, you can also make each of these VIs click. If it was not click, we can make it click. It does not matter. So we have in multicolored click, we are given k color classes. Say those color classes are V1, V2, Vk. Those set of vertices in the color classes are V1, V2, Vk. Then this is how we will go. Make each of these Vi click. Okay. For each of these Vi, add vertex Xi, Yi, and make them adjacent to every vertex in Vi. Okay. And for each of the edge which is going across from Vi to Vj, add a new vertex, make it adjacent to endpoints. This is my construction. This is the complete construction. Okay. So now my question is, let's look in the dominating set terminologies. So if I have to dominate this vertex Xi, Yi, what all my options are? Select Xi, select Yi, or select a vertex from Vi. Right? Can we see what is better? Taking vertices from Vi. Right? Because some of these Wi can also be, this We type of vertices can also be dominated by selecting some vertices in Vi. Right? Okay. Now one more question is, should we take We into solutions, any We? We are only allowing k-size solution. Does it make sense to pick this vertices Wi's into solution? It's better to pick from Vi's again, right? But yeah, we are forced to pick. So that firstly because of budget, and secondly because of Xi, Yi. Yes. So to cover, yes, we are. Right, I missed this part. So, okay, sorry. I think I have made a mistake in the saying the construction. We are not making We adjacent to both the endpoints. We are making it adjacent to everything except the endpoints. Okay, so sorry about that confusion. So, huh. Yes, but I said it wrong. Okay, so I said it wrong. What is written is correct. So for an edge UV, we are making it everything adjacent to U and everything adjacent to V. So vertex is adjacent to everything in those Vi and Vj except the endpoints. So I hope I said it correct now. So we have three things in the construction. These Xi, Yi vertices, which are adjacent to these Vi's. Vi's are forming a clique. We have added all the edges. And to all the cross edges, we subdivide them by a new vertex. And not subdivide, we introduce a new vertex and make it adjacent to everything except the endpoints. Okay? Okay. So first thing is to dominate Xi, Yi. We should pick something from Vi because it makes sense to pick Vi better than Xi, Yi. So which is forcing us to pick one vertex from each of the Vi's. Okay, one thing. Second thing is, if we want to dominate this vertex We, okay, then we cannot select these vertices U and V. They can only be dominated if we select something other than UV. Right? So imagine that I have selected this UV vertices simultaneously. So U from Vi and V from Vj in my solution. But then what I'm saying that who would have dominated E vertex? For the budget purpose, I can select only one vertex from Vi, which I said okay U. From Vj, I can select only one vertex, which I said V. Right? But then I'm not selecting any other vertices which were sent to We. Right? So, it is like we cannot select of them simultaneously. If I'm taking U from here, then in order to dominate We, we should pick something other than V. Right? Okay. So this is the idea we are using. So let's try to prove the correctness now. Okay. So if I have a k-size independent set, okay, it will be a multicolored independent set. So each of the color class have that vertex into the solution. Now let's see how we can construct a dominating set of size k. Okay, let us take the same vertices. Same vertices. You can see that each xi yi is dominated, right? Okay. Each of these vi's are completely dominated because they are clique. Now, since our vertex set is an independent set, we have never done this that for any vertex WE, both of its neighbor, any vertex WE, E was an edge and both UV is in solution because we have an independent set. So therefore, for this WE, if its one endpoint is in solution, one other endpoint will not be in solution for HE. So this is also dominated. All the WEs are dominated, right? So we are actually finding a dominating set here. And in the backward direction, if we have a dominating set here, then by the same property that we have to dominate WEs, and therefore we wouldn't have taken UV together in solution. So whatever our solution will be an independent set in my original graph G. Right? Okay. So therefore, we are able to say that dominating set problem is also hard. That's all. Thank you. Any questions?